we will start. We will have two talks today. One by Michael Huelsman. This is going to be a talk reporting results that he obtained working under my tutelage, in a sense, when studying preference reasoning. And then Christina will have another talk. I read the abstract and the talk, but I don't remember the title right now. So we will introduce Christina in an appropriate way when this talk is over. And Michael, we are behind schedule, so maybe you will try to finish by 4:30. And if you need 2 more minutes, that's fine, but try to make it prompt.
Okay.
All right, go ahead.
Okay, so as Dr. Trzynski said, this is work that we did about the role of model selection on preference learning. So kind of as a general overview, what kind of problem we're talking about. So for our setting, we have a set of choices made by a particular agent. These choices are between two objects that are similar, so two cars, two pizzas, two hotels, something where preference comes into play. And what we want to do is be able to predict future choices. So in other words, we want to learn the agent's preferences, right? That's really what we're looking at doing. And so if you break down the learning process in a very generic manner, right, you kind of get these 3 steps. So the first step is we select a representation, so some way of modeling an agent's behavior. We build a model of that type of representation using the examples that we have as a guide. And then finally, we use that model to approximate the agent's preferences and determine their future choices, right? So what we're really focusing on in this particular work is selecting a type of representation and how does that affect our ability to learn, right? So as a general overview for what we're talking about when we talk about alternatives, preferences, all this stuff, agents have preferences and they're expressed as orderings over alternatives. Alternatives are just the different choices you can make, right? So if we had 3 alternatives, let's call them A, B, and C, we could have any of these 3 different types of orderings, right? We could say A is the best, and then B, and then C, or we could do B, then A, then C, right? And we can even have things like equivalency. So A, in this third example here, A and B are equally preferred, but they're both preferred to C. And in fact, we can even have cases where we have kind of an apples and oranges situation where we can't really compare things, right? Where alternatives are incomparable. Specifically for our purposes, we're looking at what are called combinatorial domains. And so that's when we describe objects based on the values that they take on certain attributes of interest rather than by just giving them unique names. So a real simple example of this, let's say we're ordering pizza and there are 3 possible toppings, either extra cheese, pepperoni, or mushrooms. And we can either have each topping or not have it. So each of these attributes are binary in nature. So we can describe a pizza as a binary triple. So for example, the triple 101 is a pizza that has extra cheese and mushrooms. And we assume binary in most cases, and it just makes a lot of the things work easier, but we could imagine worlds where we have multiple values for a particular attribute. We just happen to deal with binary mostly, and that's the way the literature handles it. So a key thing is that if we look at all possible pizzas, right, in our example, there are going to be 8 because there's 2 to the 3 possible alternatives. And in general, combinatorial domains are exponential in size with respect to the number of attributes. So we would like to express preferences over these combinatorial domains. But since they're of exponential size, it gets a little tricky because we can't just list them out in an order. Like if 8 pizzas we could probably do, but say we had 10 binary attributes, we'd have 1,000 things that you'd have to order, right? So it's not memory efficient. And if we elicit these preferences from a person, you can probably tell me your top 5 favorite films, but you can't order all of Netflix in one sitting, right? So really what we need is some compact way of representing preferences, and then we can learn and manipulate those. So we deal with a couple of those. Starting out here, we're looking at what are called lexicographic preference models, or LPMs for short. So these have a couple of components. The first component is the attributes are ordered by importance. Then also there is an order for each domain of each attribute. And the way that we determine preferences, we consider alternatives based on the attribute importance order. So simple little example here using our pizza domain. If extra cheese is the most important, and then pepperoni is important, and then mushrooms are important, and for each domain, so for extra cheese, we want extra cheese rather than no extra cheese. We don't want pepperoni instead of pepperoni, and we want mushrooms instead of no pepperoni, or no mushrooms, excuse me. It produces the following order, right? With a extra cheese, no pepperoni, and mushrooms pizza being the most preferred option. And what's important to note in for LPMs is that we have this linear order, right? So there's no equivalencies. The way that the models are specified, there can't be equivalencies, and everything is comparable to everything else. So another representation that we use is what's called a preference formula. And so this consists of a set of ranked Boolean formulas, phi 1 to all the way to k, and we can specify whatever k we want. And we assign alternatives ranks based on the formula that it satisfies with the lowest rank. So if we had an alternative, it satisfies phi sub 2 and phi sub 5, we would give it rank 2. And we prefer things with lower ranks. So rank 1 is better than everything else, for example. Of course, we could always have an alternative which doesn't satisfy any of our Boolean formulas, and we mark that as irrelevant. Now, there are multiple ways to handle irrelevancy, but we use the simple way of just saying that it has rank k plus 1. Basically, if it's not specified in any of the Boolean formulas, we don't care about it, just throw it at the end. Okay, so given a combinatorial domain, how do we build these Boolean formulas, right? So generally speaking, we build them using atoms. And what is an atom? An atom is an attribute value pair. So for example, the atom x sub 1, 2 is true when an alternative has the value of 2 for the attribute 1. Of course, we can also negate these atoms and combine them in the normal ways that you would find in a Boolean formula. So we can have not x sub 5, 1, which is true when an alternative does not have the value 1 for attribute 5. Okay, so here's a very rudimentary, simple example. Basically, our first formula, our rank 1 formula, is that it's a pizza with cheese and mushrooms, or a pizza without cheese and with mushrooms. And our second formula is simply, does it have pepperoni? And so what's interesting here compared to LPMs is that we have these large equivalence classes, right? We have 3, 1 for each formula, and then we have this last one for all the irrelevant stuff. But we can still compare everything in a preference formula, which is interesting. And specifically, when we're talking about the preference formulas that we're using, we have some restrictions. This is mainly from a software perspective and to make our stuff run relatively easily. So the first thing is that formulas are expressed in disjunctive normal form. That's an or of ands. And part of the reason for this is that there's kind of a linguistic argument where if you're describing the pizzas that you want, you usually say, I want one with olives and mushrooms and pepperoni, or I want one with just extra cheese, right? Rather than potentially the more complicated version where you could specify them using, say, conjunctive normal form, but then you'd have to say, I want olives or pepperoni or mushrooms and and blah, 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 right? Linguistically, it's more confusing. Anyway, moving on, we also pre-specify the length of our preference formulas given by a triple IJK, which is its type. So I is the number of clauses, and then J is the number of literals per clause, and then K is the number of ranks or the number of formulas. We can further complicate preference formulas by grabbing a collection of them. So when we have a collection of preference formulas, we call it a preference theory. And instead of having a single rank for each alternative, we now have a vector of ranks, one entry for each preference formula we have in the collection. And typically these are called satisfaction vectors. And then preference is determined by Pareto dominance. What that means is that A is preferred to B if for every entry in the satisfaction vector of A, that entry is at least as good as the corresponding entry in the satisfaction vector of B. And for one entry in A, that value is strictly better than the corresponding one in B. And so we can also further complicate preference theories by ranking the preference formulas from most to least important. And the way that works out with preferences is basically we evaluate the alternatives on all the preference formulas are rank 1, and then rank 2, and then rank 3. If we only go to the next subsequent rank if they're equivalent on the previous rank. Okay, so we now have preference theories, and if we add ranks, we have ranked preference theories. But we also add in restrictions to pre-specify their length. So what that means is basically that we add 2 elements to a preference formula type triple, and those are A and B. A is simply the number of ranks for the preference formulas, and B is the number of preference formulas for ranks. So this gives us a 5-tuple for the type A, B, I, J, K. And then finally, the final representation we use is neural networks. So it's not a formal model for preference reasoning. It's not widely used in the literature, but we decided to explore whether you could learn preferences with a neural network. And the way we set this up, and we're not claiming to be super experts, is that we have an input layer where we can basically stack 2 alternatives on top of each other and send them into the neural network. And then we have a number of hidden layers. For our experiments, we set the layer size to 256 elements. The main reason that we did this was because that's the same as the number of alternatives that we have. Just kind of pluck that number out of thin air, basically. And then we tried between 0 and 3 hidden layers just to test how expanding the depth of the neural network would affect our ability to learn. And finally, the way that we're actually determining preference is that given 2 alternatives, the neural network outputs a class label that describes the relation between the inputs. So it can say, the first one is strictly better than the second one, they're equivalent, the second one's strictly better, or in some cases, they're incomparable, right? They're apples and oranges. So a little aside before we get into the experiments. Is that we looked at the complexity of learning the best LPM, preference formula, and preference theory. Now, LPMs have already been proven in the literature to be NP complete to learn the best from a set of examples. We proved that learning a preference formula or a preference theory is also NP complete for learning the best one from a set of examples. So these are problems that are NP complete, so we're having to learn approximations of the best possible, right? So in our experiments, we followed a general 3-step protocol. We generate a model of a given type of preference representation. In our cases, we either generated a lexicographic preference model, a preference formula, or a CP-net. Now, CP-nets we didn't go into, but they're a common representation in the literature. That's why we include them here. And then we use that model to generate a whole bunch of examples. And then we use those examples to learn a preference representation of one of these types. So either an LPM, a preference formula, a ranked preference theory, or a neural network. Okay, so when we talk about how we learn things, for LPMs, we used a greedy algorithm from the literature. For preference formulas and ranked preference theories, we used a simulated annealing approach that we developed basically the way that preference formulas and ranked preference theories can be applied to, or simulated annealing can be applied to learning those. And then finally, for neural networks, we basically just set up simple linear feed forward networks in PyTorch. Nothing super complicated, if I'm being honest. So let's get into some of the results that we're seeing. So each of the entries here is the proportion of examples satisfied for the average agent, and this is averaged over a number of runs. And so each row is generated by a particular type. So for example, this top row here and this top row here, we generated using an LPM. And then each column is what we use to learn, what we learned, right? So here we're learning an LPM, here we're learning a 113 PF, right? So the kind of easy trend that we can see is that we have kind of this nice diagonal where if you're learning from something, you should probably learn the same thing, right? So learning an LPM, it's best to learn an LPM. Learning a 113 preference formula, it's best to learn a 113 preference formula. But of course, we didn't just do training. We also used fivefold cross-validation to take a chunk of the examples, have them be unseen so that we could then test how well these generalize. What we saw when we go to validation is that the kind of diagonal effect is a little bit more pronounced here. But what's even more interesting is that when we look at, say, neural networks or ranked preference theories, in general, they tend to do better independent of what we're dealing with. So, for example, LPMs are really great when you're learning LPMs, but they're not that great when you're learning anything else, right? So kind of the takeaway from these single agent cases is that it's best to learn a model which is the same type as were used to generate the examples, which is kind of a no-brainer, but it's good to have that confirmed. Ranked preference theories and neural networks kind of work as the best general preference learners. So of course, there's also the complicating question, what if we want to learn group preferences, right? Well, the first thing we have to do is we have to figure out how we're going to measure satisfaction, right? So what does it mean to have a good group preference? So we look at two ways in this work. So the first is utilitarian. Basically, that says we just lump all the examples together and just try and get as many of them satisfied as possible. We really don't care for agents or anything. So it's basically just a larger version of the single agent case. And then Maximin, what we're trying to do there is we want to maximize the number of examples satisfied for the least satisfied agent. So the worst off person is as well off as they can be. The complexity for both utilitarian and Maximin are the same as for the single agent cases, i.e. they're NP complete for pretty much everything that we're looking at here. Utilitarian, that's very easy to see because it's just a larger version of single agent, but it holds even with Maximin. And so looking at our training results for utilitarian, we see that in this case, the neural networks seem to be doing the best, right? Because this is probably due to the fact that preference formulas, lexicographic preference models, and ranked preference theories, they produce orders that are transitive or total orders or that sort of thing, and they don't do well with conflicting information. And obviously, when you have multiple agents, you're going to have potentially conflicting information. And so neural nets don't have as many restrictions placed on the orders that they can produce. So obviously, neural nets are going to perform very well, and they do perform very well in training in this case. The problem comes when we go to the validation. So when we look at how well these generalize, we see that neural nets actually basically drop like a stone in most cases, except for this zero CPNet case, which is a special case of CPNets that have no dependencies, and therefore most of their examples are of one type, so you can kind of just like dartboard and get a reasonably good accuracy. But anyway, so what we see is that neural networks really don't generalize well in the utilitarian case. But we still have our little diagonal. So in the utilitarian case, learn what was used to generate it, basically, is what we're seeing. So overall conclusions, we have less accuracy in the single agent case. To be expected, we have conflicts, right? Similar validation performance for everything except neural networks. So single agent to multi-agent is basically the same for utilitarian, except with neural networks who have a worse drop of performance between training and validation. And then finally, for this, neural networks and ranked preference theories are still the best all-arounders. There's really no getting around that in this example. Now, looking at Maximin, first we have to do a little aside. We are unaware of any Maximin learning algorithm for neural networks. There might be one that we're just not aware of, and I would be very interested if anybody has one. So what we did, because we can't train them using Maximin, we trained them using the same as we've done before in the utilitarian case and the single agent case. And then we just evaluated them using the Maximin evaluation after we were done learning. And obviously, this is not going to be the best possible performance for neural networks, but we wanted to kind of get an interesting baseline to look at. Okay, so moving on to the training results. What we see again is the same thing as in the utilitarian case. The neural networks take it. They're generally better than everything else, right? And then when we go to validation, we see the same thing that we saw previously, except a little bit magnified, is in the neural nets lose the most between training and validation. What's really interesting is that ranked preference theories generalize better than anything else. Even learning LPMs using LPMs or preference formulas using preference formulas doesn't have the same effect that we saw in the utilitarian and single agent cases. So that's kind of interesting. And so our conclusions are neural networks don't generalize well in these cases. Ranked preference theories generally are going to have worse training accuracy than some things like neural networks, but better accuracy on unseen examples. So they're going to generalize better and be more useful in practical terms. Also, an interesting thing that we see is most of these results are what we're calling naively proportional. Basically, what that means is that each agent has at least 1/n of their example satisfied, n being the number of agents. In our examples, we used 5 agents, so anytime you see above 20% satisfied in Maximin, they're proportional, right? There are better definitions of proportional, we'll be honest. Anyway, and then finally, Maximin training to validation drop. So the drop in accuracy between training and validation is much greater than we saw in the utilitarian case. So overall, the general takeaways are, if you know the agent's preference structure, you should learn a model of that structure, which, I mean, doesn't sound like a big result, but hey, we confirmed that, which is good. Also, if you don't know the structure, then learn a neural net or a ranked preference theory, right? Obviously, unless you're aggregating, in which case, with Maximin specifically, in which case you should use a ranked preference theory. These problems on top of this are computationally difficult, so we're learning approximations, right? So there could be tweaks to the neural network hyperparameters or the simulated annealing hyperparameters, or maybe there's a slightly better version of the greedy algorithm that we use from the literature, right? We're learning approximations, so these numbers aren't necessarily set in stone. And then finally, if you're aggregating according to utilitarian principles, you should pretty much use the same thing you would use in the single agent case, right? We saw the same kind of trends. And of course, this research doesn't kind of stop here. We have some open questions. The first is, how can you train a neural network to optimize for Maximin? Is it possible? Is it, how difficult is it? Or, can we come up with a scheme that'll work? Do our results hold as we broaden their scope? So as we add more things in, more learning algorithms to learn different types of models, or we have different types of generating representations, right? Generating different types of example sets and that sort of thing. How do these results hold up as we expand? And then finally, how does this work with respect to real world data? So all of our data here is completely synthetic. So it's kind of an interesting question whether or not, real world preferences might be best represented by a ranked preference theory, or perhaps it's an LPM, right? This might give us some insight into mental processes, I guess. And that is everything. So if we have some time left or not, I'm open for questions.
Well,
Sure, we have about a minute.
Okay, good. Dr. Finkel is back. I wanted to say so. He will be in charge.
Yeah, sorry I was late.
That's okay, no problem.
But I do have a question. My usual question when I see that people are doing optimizations in order to, as a heuristic, in order to solve what would otherwise be computationally infeasible, and that is, have you tried genetic algorithms?
Yes. In fact, this work has gone through multiple phases. And originally we started by looking at specifically genetic algorithms, and then we switched over to looking at genetic algorithms and simulated annealing. And what we found in general, at least in our experiments, again, hyperparameters and everything, there could be a setting that we missed or something. But what we found is, generally speaking, simulated annealing works, has better performance, and better performance in both accuracy and time, is what we generally found. So instead of running both since we were getting better results from one, we decided to focus on simulated annealing in this case.
Thank you.
Hey, Michael. Can I ask a question? Can you hear me?
Yeah, I can hear you. Go ahead.
Yeah. Go ahead, Simone.
So I mean, there are two questions. I'll try to squish it into one. So the first one is if you plan to consider how people form opinions over time. Somehow you assume that you already know what you want to learn, but this is not always the case. Like, I don't know, if something new comes up and people interact with it, they may not have the opinion right away. And so depending on how their interaction is, they may form different opinions that then will last longer.
Yeah. So,
okay.
Just to answer the first one real quick, we take the assumption that a lot of the literature takes, which is somewhat erroneous, if we're being honest, that preferences don't change over time. So it is very likely that we learn one thing one day and then it changes the next.
Let me finish. Second question, then. Okay. So I know there is much more to say. Sorry, I know we don't have much time. So the second question is, so for example, one thing that it's usually pretty much understood is that the perception of benefit follows some sort of submodular behavior. So here you're assuming that, I don't know, if I add mushrooms to pepperoni, then I get something better than, I don't know, without pepperoni. So, but I mean, the amount of benefit that you get usually is not like modular, it decreases. So I wonder if this is something else that you would consider here.
Yeah. What this sounds like to me is more of a consideration of quantitative preference. So mainly what we focus on, especially in this work and just in my work in general, is qualitative preferences. So there is a whole giant breadth of research about quantitative preferences and things like utility functions and single pinked preferences and all that. We're focusing more on the qualitative aspects where we know that A is better than B, but we don't know how much A is better than B.
Oh, okay.
So it's just a different focus, but yes, that is a potential direction.
Okay.
Well, thanks. If you have other questions, I'm sure that they would be welcome, and Michael would be glad to answer them offline. So thank you so much, Michael. And again, apologies for attending this late.